This tightly pulled string is receiving a sharp, sudden strike. The localized impact creates a jagged, non-uniform wave that immediately ripples outward. Our goal is to predict the exact state of this wave as it travels. We need to know where every point on the string will be at any moment in the future. In physical space, this is a heavy lift. A sharp, abrupt shape like this strike contains a massive amount of localized data points, all changing at once. Tracking them requires a partial differential equation, a tool that calculates how these points interact across space and time. These physical equations are often too interconnected to solve directly. Because every point on the string pulls on its neighbor, the calculation becomes a dense, coupled problem. This diagram shows the specific constraint of our system. The string is anchored at two fixed points, 0 and L. The wave is physically trapped between these boundaries. If we stay in physical space, we have to calculate derivatives, the rates of change, at every point, while respecting those fixed ends. The math quickly becomes a mess of interconnected variables that are difficult to isolate. The standard tools of calculus hit a wall here. The equation is too mathematically taxing to handle as a single unified block of data. To find a solution, we have to change our perspective. Instead of trying to solve the problem in physical space, we shift the entire equation into what is known as frequency space. We use the Fourier transform to make this shift. It acts as a deconstruction tool, looking past the jagged exterior of the wave. This shows how the transform deconstructs that one jagged wave into a sum of many simple, uniform sine waves. Each one has its own distinct frequency and behaves with perfect regularity. By breaking the complex shape into these individual modes, we reveal that the chaos on the string is actually just many simple patterns overlapping. We do this because of how derivatives act on sine waves. The slope of a sine curve is just another sine curve of the same frequency. In frequency space, messy physical derivatives become basic multiplication. Reduced to simple scaling factors, the complex coupled equation fractures. It collapses into the infinite family of independent ordinary differential equations, one for every frequency mode. This completely separates the variables. Instead of solving one large, interconnected problem, we solve for each frequency mode one at a time, almost as if the others didn't even exist. The Fourier transform doesn't just simplify the math, it changes the nature of the problem, replacing a difficult calculus puzzle with a series of basic algebraic ones. However, we still have to ensure our math matches the physical reality of the string being pinned at 0 and L. A standard Fourier transform is designed for a world without ends. Because our string is bounded, we use a specific variation, the Fourier sine series. Sine waves are uniquely suited for this geometry. They naturally cross the 0 axis at perfectly regular intervals. We align these natural 0 points to lock perfectly into the physical boundaries of our string. This ensures every frequency mode automatically stays pinned to 0 at the ends. Using the sine series isn't just a preference, it's how we force our mathematical model to obey the rigid geometry of the real world. Now that we've solved for each frequency mode individually, we have to bring that data back from frequency space into the world we can see. This diagram shows the reassembly. We take those solved independent modes and add them back together into a single unified sum. This reconstituted shape moves exactly like the real string. We bypass the difficult coupled calculus to predict future motion. We were able to track this movement because we completely stopped trying to solve the system as a whole. By looking at underlying modes, we turned a dense network into a collection of independent parts. The Fourier transform shows that even the most complex physical behavior can be understood by stepping into a different coordinate system, one where the most fundamental components of the system are allowed to stand on their own.